So for pages 4 and 5 in the Unit P packet, we're looking at parametric equations and curves, specifically just a refresher on how to graph parametrics, really what they are, and how to create their graphs. So the objective: learn the definition, function, and function of parametric equations. Plane curves are paths of motion, so any kind of path that you might graph in space could be the path in which an object is in motion. All right, so we call those plane curves. So most of the time in the past, it would be in the cases of x and y. So an equation that solve for x in terms of y, solve for y in terms of x. Now what we're going to do is we're going to take those equations and introduce a parameter. That parameter would be a new variable. Most of the time it's time, but sometimes it's other variables. All right, so we can use those equations to describe blank an object has been or is going, yet we cannot tell you blank it will be at a particular location. All right, so those old school functions could tell you where they were, but couldn't tell you anything about when they would be there. All right. In order to be able to tell when an object is at a certain location, we need to find the third variable called a parameter. Where the variables x and y describing the location of the object become functions of the parameter themselves. All right, so we can determine the horizontal position, the x value, based off of how much time has elapsed, and we can determine the vertical positioning, or the y value, also based off of the amount of time that's elapsed. All right, so here below you can see that there's an example that gives a rectangular equation, so an old school y equals something in terms of x equation, a parabola, and then the corresponding parametrics, which we're going to talk about. We'll get into how you go from one form to the other, but for now it's just a matter of learning how to graph one as opposed to the other. All right, so the example: find the position when t is equal to 1 and 2. So we would need to evaluate each of these equations when t is equal to 1 and when t is equal to 2. All right, so I'd be looking for x of 1 and y of 1. All right, that's going to be, if I plug in a 1, I'm looking at 24 radical 2. All right, and if I plug in a 1 for the y equation, it's going to be negative 16 plus 24 radical 2. So my position would be 24 radical 2, comma, negative 16 plus 24 radical 2. All right. Now, if I want to evaluate it from when x is equal to 2, same idea, but you can see how this could get very tedious and also complicated depending on the type of function you're working with. All right, so if I plug in a 2, we're looking at 48 radical 2. And then we're looking at, well, 2 squared is 4, so negative 64 plus 48 radical 2. All right, so one of the many times in this course where I will not have left myself enough space, so I'm going to smidge things over. So we're looking at the ordered pair of 48 radical 2, comma, negative 64 plus 48 radical 2. All right, so there's the natural question that has got to be on somebody's mind of, well, I remember in my class last semester or last year or whatever, we were able to use the graphing calculator to do a lot of this stuff. And I would say, yeah, that sounds great. We're not going to use the TI graphing calculator because it's antiquated. It had its place, and there was a good use for it, but it's now just a money grab. So we're going to go with the free, better option, which is the Desmos calculator. All right, so it can handle both rectangular and parametric equations. So I can put in the original function. Now I already know what it looks like, so I'm not going to bother with that. If I want to put in the parametric, what I would have to do, and it's very simple, I would just take whatever x is and whatever y is in variable form, so in Desmos, I would input that in as an ordered pair. So 24 radical 2 times t, comma, negative 16t squared plus 24 radical 2 times t. All right, so 24 radical 2 times t, comma, well, I still want to stay in the parentheses, comma, negative 16 t squared, so you go to the QWERTY pad to get that, squared, plus 24 radical 2, get out of that radical, times t. All right. Now, you're always going to have domain considerations, so I'm looking at this graph and I'm saying, well, it's not quite what I want, but it's almost what I want. It looks like it's shaping up to be that graph. Just I think I need to go out a little further. Yeah, 5 seems to do it. 5 probably overdid it. 3. 3 was even overdoing it. 2, not quite enough. 2.1, 2.4, 2.5. How about this? How about D and add a slider? And then just slide along until you get where you want to go. All right, that seems reasonable. All right. Then I can bring it in, and now I'm pretty comfortable with my graph. All right, so pretty nice and easy to graph these things using the Desmos calculator. All right. The equations given by x equals f of t and y equals g of t are parametric equations for c, and the parameter is t. The blank of a plane curve is the direction that the curve is being drawn. That's known as the trajectory. So when we create a parametric curve, because again, when we graph, a graph of a function is a pathway, but if we're talking about plane curves, we're talking about motion along that path. All right, so we gotta have to indicate the direction of the motion. All right, so we'll get into that in a little bit. But you could read through the instructions for sketching the plane curve and the orientation or direction, but I'm going to walk you through that process right now. So it's not a bad idea to read these two little blurbs, but we're going to tackle it right away anyway. All right, so I'm looking at a table of values and a nice looking graph grid. Now we can crunch these numbers by hand because they're not difficult. They're both parabolic. I'm sorry, they're both problems are parabolic. Both of these equations are simple. The y one even simpler. So it's just taking whatever the t value is and doubling it. So negative 4, negative 2, 0, 2, 4, and 6. That was pretty satisfying. The t squared minus 4. 4 minus 4 is 0. 1 minus 4, negative 3. Negative 4, negative 3. Back to a 0. And then a 5. All right, 9 minus 4 is 5. All right, so what we have here is an ordered pair, or a set of ordered pairs. 0, negative 4, negative 3, negative 2, negative 4, 0, negative 3, 2, 0, 4, and 5, 6. So that's what we would plot. 0, negative 4, and we're just going to double check to make sure everything's going to fit, but it looks like it will. 0, negative 4 would put me right here. Negative 3, negative 2. right here. Negative 4, 0. Negative 3, positive 2. 0, 4. And then 5, 6. All right. Now, since this graph started at an x value of 0, but more importantly, it started at a time factor of negative 2, it's going to go in this direction. Really, you're just thinking about the order in which you plotted them. As long as you're following the increasing order of t, then you'll have the orientation of the graph. Right? But even doing this, it doesn't look like I've demonstrated any kind of orientation. How does anybody know I didn't graph it the other way? You know? So what we do is we put little arrows on it to indicate the direction of the motion along the curve. All right. Now, the next one, yeah, it's the same idea, but the numbers are a little juicier. We're going to multiply all of the t values by 20. All right. So 0, 10, 20, 30. It's linear, so we're increasing by 10 every step of the way. Then 60 minus 16t squared. Well, 16 minus 0 is, 64 minus 0 is 64. 1/2 squared is a quarter. So 16 times a quarter is 4, so 64 minus 4 is 60. All right, this is not linear, so we're going to have a variable slope. 64 minus 16, because 1 squared is 1. And this is going to be 48. All right. 3/2. 3/2 squared is 9 quarters. 9 quarters times 16. So 4 goes into 16 4 times. So 9 times 4, 36. So 36 subtracted from 64 is what, 28? I might be double checking that one. Oh, 28, look at that. All right, next one would be, it looks like 0. All right, 2 squared is 4. 64 minus 64 is 0. And 2.5, well, I already typed it in the one time. So I might as well just make that a 5, so negative 36. And then a 3. We're looking at negative 80. All right, it gave us these particular values to plot, so we do have to plot them all. As unrealistic as it might seem for some of them, these are the instructions that were given us, so, graph that information. I mean, or at least the instructions that were implied. They do ask when it hits the ground. We'll get to that in a second. That we could pull right from the table. We don't need a picture, but since I'm creating the graph, might as well look at the graph also. All right, so the x values are going out to 60. I can scale this any way I want. Definitely don't want to go by ones. If I go by tens, it's going to be a little tight. So maybe I'll go by fives. So 10, 20, 30. Oh, maybe not. Maybe I won't go by fives. Let's see. 12s? Fours? No, fours would be too much, maybe. Maybe tens is the way to go. Yeah, we would need 12 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, I could go by sixes. It just seems a little, ugh. I think the better way to go is just suck it up and go by tens. All right, for the y's, we need to go as low as negative 80. So we can go by 16s. That'll get us down to a negative 80. We could also go by 20s and then do some estimation along the way. All right, so 20, 40, 60, 80. We need to get up as high as 64, 20, 40, 60, and I'll throw an 80 here also. All right, so plotting, we're going to have a 64. I'm just kind of eyeballing that one. 1060, right about there. 2048. Well, 50 would be halfway, so a little bit less than that. 30, 28, 40, and a 0. All right, that's the moment it hits the ground, which is 2 seconds. Hits the ground at the 2-second mark. All right, then 50, negative 36. It's going to put us about right around here, and then 60, negative 80. And then I can just do the best I can to not draw a terrible curve. Oh, I slipped. Oh, slipping and sliding. All right, so time increased. As time increased, I should say, the height of the object decreased till eventually it plowed through the earth, assuming it's the earth, and went subterranean. All right, but we weren't given any context here, so we don't really know what's out of bounds and what isn't. So that's pretty much where we leave it.